Alright, so we have our first beautiful internal force diagram problem here in front of us. Let's take a closer look and understand what we are supposed to do. So first of all, we have to calculate the internal forces at location B and C. That is indicated by these dots here. Those are not hinges or anything. This is just identifying the location. And then when we're done with that, we have to draw the diagrams for the normal force, the shear force, and the bending moment. But please keep in mind that this lecture is also designed around a classroom lecture, so that for time reasons I only make students calculate the internal forces here and here. What probably would be good for you would be to calculate the internal forces to the left of the 9 kilonewton meter and also to the right of the 9 kilonewton meter. Just set up the cut and the equations for that, and that will help you to draw the diagram. Due to time limitations in the classroom, even though it's a virtual classroom, I will take a shortcut when it comes to this one and I will show you how that is done. But you should practice that for sure. Some of you will be faster than others, but practice definitely makes perfect. And at the end, we all have to be fast to be prepared for the upcoming exam. All right, but let's get started and calculate the support reactions at A and B. But before we do that, take a look at the system and understand that we have 6 kilonewton pushing down here, and then we have 9 kilonewton meter rotating the system counterclockwise. What does that mean? That means that this vertical force here causes an upwards reaction here and an upwards reaction there, but on the contrary, the 9 kilonewton meter rotates this up and this down. And therefore, we need to have a reaction that at D pulls down and at A pushes against that. So obviously, the support reaction is a combination of this plus this, and we will now go ahead and calculate that. And to do that, I will first draw my free body diagram. And as always, it's a free body diagram of a rigid body. That means that I have to also include my dashed fiber. And I have, as always, my 3 support reactions. I have a horizontal reaction at A because that's where the pin is located. I have a vertical reaction here, and I have a vertical reaction at D. And I'm going to call this RDY, RAY, and RAX. And we can already say that this is equal to 0, so this is done. But I have to now bring down my forces here. And this is the 6 kilonewton. And I have to include my 9 kilonewton meter. And so that now is my entire system. The whole beam is 9 meters long, if I'm not mistaken. So yeah, 3 plus 4 plus 2 is 9. And so I can now quickly actually calculate the support reaction. If this puzzles you, please go back to the calculation for support reactions. I think we started that in lecture 10 or so, but I can just say that, for example, my RAY, and I need my numbers here from the top, so my RAY is nothing else than 6 kilonewton multiplied by 4 plus 2, if you will, right? 4 plus 2 divided by 9, that's the entire length. And then plus, because it's reacting to it, plus 9 divided by 9, so that's 9 kilonewton meters divided by 9 meters, right? And again, if that puzzles you, please go back to support reaction calculation. Of course, the other one has to be complementary, so we're looking at 6 multiplied by 3 divided by 9 minus, because I have to pull down here to keep the rotation from not rotating counterclockwise. So minus 9 divided by 9. And now I can solve this and I can find that my RAY is really equal to 5 kilonewton and my RBY is really equal to 1 kilonewton. And please keep in mind that the 1 kilonewton is really going up and the 5 kilonewton is also going up. So I don't even need to worry about flipping any signs or anything, but that is the results you should find. And now you can go ahead and actually find your internal forces through cuts. I will do that on the next page. If this confuses you, we have some room here for calculating support reactions. That's what this space is for. Go ahead and just set up the equation. Rotate about this point, rotate about that point, and you will find your equations. But I will move on now using the 5 kilonewton and the 1 kilonewton, and I will see you on the next page. On this page, I will now go ahead and draw the internal force diagrams for any location I need to find the values. So look at the headline here, and please understand that you have to calculate your internal forces via as many individual cuts as necessary. So this is different from student to student, and initially I always recommend to do like as many cuts as you possibly can. So do many cuts, but at the end you want to do it just as it's necessary for you. Of course, in this problem I'm asked to find the internal forces at location B and C, so I will now draw the free body diagram first for those. So I will draw the free body diagram for cut A to B, which, if we remember that correctly, that was just the left side of the system. So I have my free body diagram here, which how that works we really showed you in the previous lecture, but I cut it here at B, and I had support reactions which were 5 kilonewton pushing up here, 5 kilonewton, and I had a 0 here, so I don't even worry about that. But then there was no other force on the system. Remember that? There was no force except that one. And what I do next is I will bring in my internal forces that therefore become external forces. So for example, I use my little study card, which tells me that the moment goes in this direction, the shear force in that direction, and the normal force goes in that direction. So I now indicate them, and I call them M at B, V at B, and N at B. And you can already tell that due to the sum of the forces in the x direction being equal to 0, N at B is really equal to 0. I don't have to explain that. But for the sum of the forces in the y direction being equal to 0, I use upwards positive, and 0 is equal to minus positive VB plus 5 kilonewton. And so therefore my VB is really equal to 5, and that is positive 5 kilonewton. And that is a result that we will use later on. So I'm not going to double underline it here because I will just use it in my diagrams. Now for the moment, what do I do? To calculate the moment, I take the sum of the moments about point B equal to 0, counterclockwise positive in this case, and 0 is equal to plus positive MB minus 5 kilonewton with a lever arm of 3 meters. So the distance is 3 meters to point B, and negative is the rotation in the clockwise direction. So therefore I know now that my M at B is equal to plus 15 kilonewton meter. Once again a result, but I will use that result in a diagram later on. But sometimes it helps me actually so to find the values faster as I solve them. So I will actually at least single underline each of these values so that when I look for them later on, I will know where to find them. Okay, now we are ready to actually make the next cut, and the next cut was at C. And to do that, all I have to do is extend my free body diagram a little bit. So I'm going to do the free body diagram for A through C, if you will. And the way that looks like is very similar, just a tiny bit longer. So you could think of this as being 3.00001 long. And of course I have my upwards force still here, and that is 5 kilonewton still. But I also have my downwards force right here, which that was given with 6 kilonewton. And now I have to cut right at that location C and bring in my internal forces, my moment, my shear, and my normal force. So V at C, N at C, and M at C. And I can now set up my equations. Before I move on, just notice the only difference between this and this is really that we made this a tiny bit longer here and therefore now include the 6 kilonewton. All right, so now I can go ahead and calculate my internal forces at that location. So for example, the sum of the forces in the x direction is equal to 0 really tells me that NC is equal to 0. That is a result that I will use later on. I also have to find the sum of the forces in the y direction being equal to 0. And I pretty much say that 0 is equal to minus positive VC plus 5 kilonewton, that's a support reaction, minus 6 kilonewton. And now I know that my V at C is really equal to minus 1 kilonewton. And that is something I will use later on as well. And I'm ready to move on to my moment. So the moment at C is really determined through the sum of the moments about point C being equal to 0, counterclockwise positive. And 0 is equal to, I always start with my unknown, plus positive defined MC minus 5 kilonewton multiplied by 3 meters. The distance is still 3 meters there. And then I have to include the 6, but the 6 really has 0 lever arm, so you would say something like plus minus 6 kilonewton multiplied by 0 meters. That's really how that would work, but the distance again is so short that it has no effect. It would actually be positive because it would rotate counterclockwise, but let's forget about that. And let's understand that the moment at C remains plus 1.5 kilonewton meter. And that is something that I need to find later on in my diagram, so therefore I'm highlighting it as well. All right, technically we are done now according to the problem statement before we draw the internal force diagrams, but for educational purpose I want to move on from here to the concentrated moment that would be acting somewhere here, and I'm going to pull in the reference here real quick to help you understand what I'm talking about. So let's actually bring in this picture and let's now find the internal forces to the right of this moment. You can yourself determine them to the left of this moment, but for speed reasons here, I'm just going to look at that location. And to do that, I'm drawing my free body diagram of that portion. And also this will give us an opportunity to use the left cut actually. So now I'm cutting right here. And my support reaction now actually has a value of 1 kilonewton here. And I will bring in my card, the other side of the card now that I flipped into half, and you will find that the moment goes in this direction, shear force in this direction, and the normal force in that direction. And this now would be, of course, at location 7 meters to the right. So really we can call this here M at 7 to the right, V at 7 to the right, and N at 7 to the right. So let's go ahead and calculate the values. By the way, this is the free body diagram for, let's call it C, well, 7 to 9 meters, if you will. All right. And please note that I always, when I draw a free body diagram, it's always including the entire either right side or the entire left side. So I don't want to have a free body diagram that is somewhere dissected from the middle that doesn't include everything to the right or doesn't include everything to the left. You can technically do that if you really know how you do it and what you do, but for this beginning purpose, it's not a good idea to do that. So for now, always include either the entire right part of the structure or always the entire left part of the structure. So before, for B and C, we used the left side. Now I'm using the right side, and therefore I have a different cut. And now I can use the easy numbers here now. For example, the sum of the forces in x is equal to 0, and that will tell me that n at 7 to the right is really equal to 0. That is a result. And the sum of the forces in y is equal to 0. That will help me to understand that 0 is equal to, and now I'm using plus positive v7r. So that's v to the right and 2 positives because it's acting positive and it's pointing down upwards. And then plus 1 kilonewton. And so I know now that my v at 7 to the right of it is really equal to minus 1 kilonewton. And you may have already predicted that, but again, it's education here. So last but not least, I do the sum of the moments about 0.7 to the right, if you will. It's equal to 0, counterclockwise positive. And 0 is equal to, I start with my unknown, positive m7r. But that turns clockwise, therefore it's a negative rotation. And then I have to pay attention here. So this now, the 1 turns about this point counterclockwise with a lever arm of 2. So I'm using 1 kilonewton multiplied by 2 meters. And it's rotating counterclockwise. Therefore, this entire thing here is positive. And therefore, I now find that my m at 7 meters to the right is really equal to 1 times 2, right? So plus 2 kilonewton meters. And it's important that you get that right, because if you somehow messed up the sign here or the sign here or the sign here, you would not find it to be positive. And that is, of course, important in an engineering context for these problems. And again, I invite you to now draw this diagram and actually include the 9 kilonewton meters here to the left of it, and then run these equations and find the answers. But I am ready now to move on to the next page and draw all the diagrams. Let's take a final look at here what we did. So I did decide to make my cut from A to B, from A to C. That was per definition. I found my normal force, my shear force, my moment, my normal force, my shear force, my moment. And then I also decided, because I didn't know what's going on here at this location, to make another cut. And maybe if I were a beginning engineer or like somebody who hasn't had a lot of experience with these internal force diagrams, I would probably make another cut at, let's say, 8 meters, maybe somewhere at 5 meters, maybe somewhere at 1 meter, just so that I can really practice and learn how these values come about. But for me, this is enough now to really draw the diagrams, and I will do that on the next page, and I'm looking forward for you to join me there. All right, so here we can see the very nice solution page where we have the luxury that the teacher was so nice to give us the structure itself lined up with the 3 diagram bases, if you will. And I guess you're welcome. But now we have to include the values that we calculated on the previous page. It's really helpful if you take a look at the previous page, or that you have it side by side with you right now. I, of course, here have a computer screen, so I cannot have that next to me because I want to focus on this one. But believe me, I have the values right next to me as well. You just cannot see them right now. But let's go ahead and first bring down our lines here. That always helps me to line up my diagrams better. And then also the next easiest thing to do is probably to draw the indicators for the individual lines, for the individual diagrams, I should say. So of course I start with my normal force. So let's put the normal force right here. And in this case, we're dealing with kilonewton. So I have to put that unit here as well. And here it's super simple, but I still have to show it for each of my individual parts. everything here was 0. I didn't have to do any calculations. So I indicate that this is 0, this region is 0, and this region is 0. I could also call this a domain, by the way. In fact, let's do that. Let's call this here domain 1, domain 2, and domain 3. That will become more important in one of our next lectures. But now I want to move on to the shear force diagram. And for my shear force diagram, the first value that I calculated at B was equal to positive 5, if I remember this correct. So let's say this here was equal to positive 5. And then at C, I had a value of minus 1, if I'm not mistaken. So that looks like this. And for the other location where I also calculated, remember I also calculated it here, right? So somewhere at this location to the right of that line. And I found that that was also minus 1. Now, can I extrapolate my understanding from previous problems and from what I've learned as I set up the equations? Yes, I can. So what influences the shear force distribution from here to here is really only the support reaction, and remember that was actually 5. So really how I should draw my diagram would be up with 5, because that's my RAY. So this is RAY, and then after I have RAY I can move, because nothing happens, nothing happens, nothing happens, nothing happens, nothing happens. Ooh, something happens now. How much does happen? It happens with 6 down, right? So 6 down. And then again, nothing happens, nothing happens, nothing happens, nothing happens. And oh, something happens now. I have to go back up to 0. And so this is my negative region now, and this is my positive region. And notice one important thing that I will explain to you after I completed my diagram here. Notice an important thing. Number one, I forgot to indicate that it's the shear force and that it's also in kilonewton. But really what I want to put your attention to is that there's a moment here, a concentrated moment, which you see that right, there's no influence on the shear force diagram. So the concentrated moment happens to have no influence, and you can see that in your equations on the previous page. I invite you to go there and study them. But you believe me here probably that it has no impact. So I have for full points also to include that this here is equal to 5 plus 5, and this here is equal to minus 1. And now I'm already ready to move on to my moment diagram. So first let me indicate it before I forget that again. This is in kilonewton meters. And now I can find my values that I calculated first for B. What did I calculate? I calculated that to be plus 15. So let's pretend that's right there. And then at C, I also calculated it to be plus 15. So of course, in reality, it is at the line. So I'm going to erase this real quick and actually put the X directly on the line. So I pretend that this here is plus 15. And I also calculated the value right here with positive 2, so that I can actually draw a little cross right down there. And now it's very tempting to say, if it's plus 2 here, then maybe it's plus 2 on this side as well, because that was the case for this location. But notice that here at B and C, we're actually dealing with a concentrated force, whereas here we are dealing with a concentrated moment. And so the concentrated moment will have an impact on your equation if you extend the cut that we did actually for the right side of the system. In fact, you will find that then you have the 9 rotating counterclockwise and therefore going against the moment that comes from your internal force definition that is located on your little study card. So therefore, you will actually find that this bumps up the value by 9. So really what I will end up with is with another cross right up here. And remember that this value here was plus 2. And then we have plus 9. So this is plus 11. And that makes perfect sense. And you will see this when I draw the diagram. And I will repeat that then. But because you don't have it drawn when you have to go through this thinking process, let me just show it to you. So this makes perfect sense because the slope is -1, right? And to get from here to +2 is impossible with a slope of -1 over a length of 4. Instead, you have to go from 15, remember that this here was +15, right? +15 can only go to 11 over a length of 4 meters with a slope of -1. So, and notice that it's also a negative slope here. And last but not least, the thing that you always know for your moment diagrams is that here is a hinge effectively, and this acts like a hinge, so you can think of this as a hinge, and therefore the moments must be 0 there. And final observation here for the moment diagram is that if I were to make this cut here, for example, that I made for B, that the only thing that had a moment or that created a moment about point B was the support reaction. And that support reaction is dependent on the distance, and therefore if I increase my distance linearly, the moment will increase linearly. And so that's reflected here in the 5, right? So the 5 is the slope over 3 meters. And the last thing that I have to do, therefore, is actually connect my points properly. Of course, I've seen students always being able to connect them, but the question is, can they connect them properly? And so I have the first one, and then the next easier one is probably the one down here. So that one. And then I have a last sloped line. And important here to understand, and that's the educational lesson of this problem, is that I also have to make this connection. And so you understand that this jump here is really +9. +9, be careful, you cannot always say because it's clockwise or counterclockwise, therefore it's plus. It really depends on the cut and the system. So please use that with caution, but also make sure that you indicate what your area is or where your positive area is, and indicate your significant values, right? So these are the significant values here, because those are the values where something changes. And please note one thing. Yes, we said before that V is equal to dm dx. That is something that you memorize from now on for good, because it's very important. And it is true, but remember the problem that you have if you do it the other way around. So what do you do from the shear force to the moment? You actually integrate in this direction, right? So in fact, I kind of, in my head, without telling you, although you probably noticed it, I integrated when I drew this line, right? I said that this line must have a slope of -1, or this line has a slope of +5. And so students are very tempted to take a look at this diagram and then just in their head integrate to draw these. But you would see this would not work out if you would not consider this jump here, the 9 kilonewton meters, right? So you can think of this 9 kilonewton meters actually as an initial or boundary condition here if you do the integration. So please be careful when you just integrate from the shear force to the moment diagram. You find this often recommended to you in the literature, and this is of course correct, but you have to understand the entire physical meaning of the system. And here is just one example of that, where you see a concentrated moment, and that has an impact on your diagram that you would not find by simply integrating these functions here, the +5 and the -1, where the function is a constant. I understand that, of course. But this now completes our entire diagram, and we of course understand the general relationship here. For example, the maximum moment is located where the shear force passes through 0. We have the connection of the slope to the shear force magnitude here, and therefore we applied our knowledge one more time. And I think that concludes our lecture, and we can now move on to the final page and summarize our findings.